Welcome. I'm gonna go over the homeworks from Convolutions, our last homework session. So number 2K, so they ask the Laplace transform of the following function, which is given as an integral. So the integral is from 0 to t, tau to the power, tau. I'm gonna stick with my z here. You don't have to, but since I started using z, I'll keep using z here. E minus t minus z sine 3t minus z dz. Okay, so got it right? I think so. So before I go on, remind there are two important formulas here that we in this section, in this chapter, is first of all the convolution itself. How do we define the convolution? And that is given by fz gt minus z dz. So it's an integral where you have the product, but the thing is that there's a shift here of the variables, or a change of variables perhaps. And then the second important thing is that the Laplace transform of this convolution product is the usual product of the Laplace transforms. And the way that we often use it is, well, okay, here, how are we going to use it in here? We're going to use this formula here by recognizing that this integral that is written down there is actually a convolution. So it's an indirect way, right? So we have this integral, we say, oh, this integral is what convolutions look like. So let's say, what is this the convolution of? What we're looking for is, well, there are two functions, it's a product of two products, so we have three factors here. What goes where? Which is f, what is g? Well, f is those things that depend on z. G will everything that has to depend on t minus z. So luckily they have written it for us in the right form. Sometimes they can fool you. For instance, if they would have expanded this thing here, then you would have an e minus t and an e to the z, and then you say, oh, the e to the z goes back with this one, but then the e minus t. Well, okay, you could have taken that out then. So you see that you can manipulate this a little bit, right? Because since we are integrating with z, we could take this e minus t z t out. We could expand this. Let's not do this. Okay, let's just stick with what they give us. Okay, so we have to recognize this as a convolution product. What I just said is the pure power, the function just of z, that is t to the sixth. Now remember, yeah, and these functions are functions in t, right? So that's why I have to write it as a function of t. And also this one is where in g we plug in t minus z, but the original variable was t for us, so we're going to do that the same thing, and that would be these two together, right? So that would be e star, that's the other one now, that's minus t sine 3t. I repeat, so we look at, let me perhaps color it somehow. Let me go to a little lighter color here. No. So what I mean to say is this t minus z, t minus z, this becomes the t, that becomes t. That's this t and this t, okay? That is how you go somehow backwards from the integral to the convolution product. Okay, so this is equal to that. And what they ask us, the original question was, what is the Laplace transform of this one? So what is the Laplace transform of that one? Now we're going to use this formula. It says that, so we have to take the Laplace transform. That is what they're asking us to do. So that is the Laplace transform of t to the sixth times the Laplace transform of e to the minus t sine 3t. Okay, that is using the product, the convolution theorem. Great. Now, each of these are actually really something that is on the tables, but let's try to just memorize them. T to the power 6, that will be 1 over s to the power 1 higher, 7, right? But you have to multiply it with the factorial of the previous, of the actual original power, 6 factorial. What is this guy? Well, the E is a shift in the sign. So let's analyze a little bit. We have an omega that is 3 here, and an A. What is A here? -1, right? Okay. So let's do the sign first. The sign has the omega on top, and then we have here the variable squared plus omega squared. Don't forget it's omega squared in the denominator. But I don't write S here because I still have to shift by 1. So S minus 1, that is S plus 1. Okay? And this is the answer. So the answer is, if you want to put it together, is 3 times 6 factorial over S to the power 7 times S plus 1 to the power squared plus 9. Okay. Okay. But we, in principle, in theory, we can now find the inverse Laplace of this guy, but it would be quite difficult to find the partial fraction. If we would have the partial fraction, then we can do the inverse Laplace, and we would actually know what this integral is equal to. Okay, so in theory, this is a theoretical way of calculating this, as I said, difficult integral. These so-called convolution integrals, and they are called thus because they are convolution products. These are in general very difficult, and that's why in the rest of the thing we will never solve them. Okay, so let's look at the next question. Number 3E I had assigned. So here we have to solve a differential equation, y double prime plus 6y prime plus 9y equals ft. So here the f is the one that we don't know, and we will have to give the answer in terms of an integral involving f. But we have also initial conditions. y0 is 0, and y prime 0 is y prime 0 is, what am I doing? E is -2. Okay. So what we do is we take Laplace on both. Let's call the Laplace of little f capital F. The standard thing to do. And then what we have to also see what is here happening. Laplace of this guy plus 6 times Laplace of this guy plus 9 times the Laplace of this guy. And that is then equal to f. Okay? And we're going to take the Laplace of little y, we're going to call that capital Y. We follow this convention of replacing lowercase into higher in uppercase to denote the Laplace. Well, okay. Now there are formulas now. This one, I hope you can look them up. I'm just going to quote them, right? This is s squared y minus s times y0, which is 0, s times 0, minus y prime, so plus 2, plus 6 times sy minus 0, the y0, right? This is because this is 0, right? Plus 9 times y, and that is capital F. Okay? So what we have? We have s squared plus 6s plus 9y. And what is the remaining terms? There's not much. There's only 2. Plus 2 equals f. Right? Right? This is 0. Yeah, that's the only one that's left. So we bring the 2 to the other side, so it becomes -2. That will allow me to do it this way. And now we're going to divide by the denominator. Y is equal to f over s squared plus 6s plus 9 minus 2 s squared plus 6s plus 9. Okay. And it is here perhaps that you might feel lost. And so let me explain. We have two, in general, this is general thing, if you do several exercises, you'll see you have one where there's an f in, and one where we just have a partial fraction. This one we can just write down, the partial fraction. This one we cannot because we don't know what capital F is. Capital F doesn't have to be a polynomial at all, so to talk about our partial fraction is crazy in some sense. So what are we going to do? Let me explain this one. This is something that we know from 8.3. So let me explain what is going on here. So what we're going to do is we think of this as a product of f times 1 over this function. Okay, so let me write it. I'm thinking this as f times 1 over this guy. Now, since I'm going to have to do this, because in this part I have to write it as a partial fraction, right? I need to factor this. So this it's either quadratically reducible or it can factor. In this case, it actually factors as s plus 3 squared. Again, that's a special situation where we have a single root, multiplicity 2. Okay, so s plus 3 squared. Okay, so and then minus this one, I'll also write it here, s plus 3 squared. Okay, so what do we do with this one? So I'm writing it as a product, okay, and this is the Laplace of little f. The question is, what is this the Laplace of? Okay, so we're looking for the little g. You think of this as capital G, so we think of this as, this is the capital G, and so the question is, what is little g then, that corresponds to it, right? We know what corresponds to capital F, little f, which we don't know, but it is some function. So what is there? Well, that's easy, right? It's the inverse Laplace. We can find out. To answer what is g is actually easy. So let's do this. G is, just from our tables, let's think about it. We have a power here, and at the side of the Laplace, the power is 1 higher than on the other side. So we have here, we're going to have the power 1, okay, t to the 1. But there's also a shift, and what is the shift here? A is negative 3, right, minus minus. So this will result in a multiplication with this exponential function, e to the minus 3t. Okay, so are you with me? So what we have, what does this say? I repeat, this little f, which we don't know what it is, has Laplace capital F. We now figured out that e to the minus 3t has this as Laplace. And we now use this thing here, that the Laplace of these two, the product of the Laplace is the Laplace of the convolution. What we really use is actually this, that the convolution is the inverse Laplace of the product of the Laplace. So that's how we would write it down. But more importantly, what are you doing? So think about it. What you're doing is you're saying, okay, I know that this thing is, being a product, is the Laplace of a convolution. So the inverse Laplace, because that's what we're going to try to do, right? What we're looking for at this stage? We're looking for the inverse Laplace. Why? Because the inverse Laplace, if I do this inverse Laplace here, I get little y, and that's what I want. Okay, so I do the inverse Laplace on this one, and we know that this is then f convoluted, let's say f star g. Okay, and we know what f star g is. We can write that down, right? So I'm writing this part out. So f star g is just this integral. This is just copying the formula. So now we copy this formula, and that is from 0 to t, ft. Remember, you plug in t. Sorry, not t, not t. T? No, not t, right? Z. And what do you plug in g? T minus z. So that would be e to the minus 3 t minus z, t minus z. Now, be careful, we're replacing t by t minus z, but we should put parentheses around it, not because we're multiplying everything. dz. So this is the integral that represents that part of the solution. There's a second part of the solution. Let's work that out quickly. What do we know about this guy? So now I'm going to work on this fraction. We know it's going to be a over s plus 3 plus b over s plus 3. Oh, that would make sense, right? Because twice the same. No, because it's a multiplicity 2, we have to go to 1 power higher. We go until the power that the multiplicity is. Okay. And can we do Heaviside? No, because they have double roots here. Multiple roots with multiplicity 1. They're not distinct roots. So we have to expand this. So I'm going to do this here. So we have minus 2 s plus 3 squared. Oh, but right, what I'm doing, right? Sorry. Is this, now, if once you write this down, you realize, yeah, but this actually is a Laplace, because it's this one. So the a here would be 0. There's no need to do the calculation, because the calculation is just going to tell you this, that a is 0 and b is 2. So no need to do this. Okay, so this is quicker even. So we have here what we want. Why? Because we know exactly what the inverse Laplace of this thing is. So here, remember, that was the blue thing, or the blue arrow that I was drawing. Let me draw it again as an arrow. So, yeah, I wrote here equal, but it's actually right. So what we said is that y is equal to this thing minus 2 times the inverse Laplace of this, which we can write down very quickly because we actually did it already. That is e minus 3t t. Right? We did this already. So this is the solution. So one part is an integral, the other part is just a function. And that is how these questions have to be answered. It's a bit weird that the answer is not fully unsatisfying, right? Why don't we calculate this integral? Well, the reason is that if you put there a general function f, that these integrals are very hard to calculate. So this was 8 point, I want to double check that I have no copy error here, 8.63 yep, that's what it is. Okay, and just for the fun of it, I didn't assign it, but let's do one more question. I want to do 5b. Well, I assigned the homework, but I didn't list it as a special problem. Where am I? Here. 5b is they ask you to calculate this integral. 0t, t minus z, I'm going to again write z, 13 z to the 7th dz. So the idea is now always the same. The idea is the same as in the first question, right? We find the Laplace transform of this function, but then you realize what you get is something of which you can calculate the inverse Laplace transform, and therefore you would have actually what this is. So step 1, like we did in question number 2, the first thing we needed to do is write this integral as a convolution. Because this is called a convolution integral. You have to recognize this, right? Why is it a convolution integral? Because some factor is a function in z, and the other factor is a function in t minus z. And what are these two factors? Well, t to the 7th, remember, I don't use the variable z. I use the variable t for both of these functions now. And what is the second factor? Well, the 13th power, t to the 13th. Okay? Again, okay, I agree that this is the variable inside the integral, but that is the substitution you have to do when you do the convolution. In the second function, you plug in t minus z. In the first function, you plug in z. Little thing that we mentioned, but we don't need it really, but is that you could switch the roles of f and g, and of course then the roles of f and g would be switched here. It's not really important, so let's not bother about it. We can write it this way. Why do we do this? Well, we know that the Laplace of this thing, now we're going to take Laplace, okay? So I'm going to take the Laplace, and what we know is that the Laplace of this guy will be the Laplace, I'll write it down, t to the 7th star t to the 13th is the Laplace of t to the 7th times the Laplace of t to the 13th. That is exactly using my second formula now, okay? But that's not so bad. I don't know why I wrote this all the way in the corner here. That's going to make my life hard, so. Why is this keeping... Okay. Now let's get rid of this error here. Okay, so that's what I'm doing, right? So I'm taking the Laplace here. And this is easy, because these are just powers of t, and we know what they are. That is 1 over s to the power 1 higher. But on top we have to put the 7 factorial times, and here we have to put the 13 factorial and s to the power 14. Okay, so now we work this out. This is very simple algebra. This is something your nephew can do, your little nephew can do, right? It's s to the power 22. And now we're going to do and what we now want to do is go back and take the inverse Laplace, because that will give us the answer that we want. This will give us the integral. Now, in order to do that, we know that the inverse Laplace, so sorry, although I pointed upwards, let me keep going downwards here. What is the inverse Laplace? Well, we know it's going to be t to the power 21, okay? But if I take the Laplace of t to 21, I get actually a 21 factorial in the numerator, divided by s to the 22. So I'm just preparing myself for that. 13 factorial over 21 factorial times 21 factorial times s to the 22. So what I'm doing is I'm dividing I'm multiplying top and bottom with 21 factorial, so that this is exactly the Laplace of this guy, and then this is just a coefficient that I can take out. So 7 factorial, 13 factorial over 21 factorial times t to the 21. So extremely quick, right? Once you know how these things work. Okay, so there will be also a quiz on this one, and that will be, or at least this will be on the final. Let me put it that way. I'm sorry, about the quiz, I still have not made up my mind exactly what we're going to do for the quiz, but it will definitely be on the final.